Hey Huskies, we have another video about growing. This one is going to be more about growth rate and growth factor, and we're also going to be comparing linear with exponential. So I can find the growth rate and the growth factor and use them to write exponential equations. And remember that exponential is like geometric, that all those geometric sequences we learned about can be modeled by an exponential equation, and also that arithmetic would equal linear. Okay, so our classwork starts right off with this story about Cassidy and Kaylee, who are sisters, and they have a nice grandma who gives them some money. And she invests the money in a bond. That is a thing that you're putting it in the bank and you're not touching it. You're promising not to take any money out for 10 whole years. But it's going to earn interest while it's in there. And so it's going to earn 4%, and she's going to leave it for 10 years. And she gives Cassidy $1,250, but she is so nice, she gives Kaylee twice as much. Does this grandma love Kaylee twice as much? Well, let's figure this out. So let's write an equation for Cassidy. It says write an explicit equation to show the relationship. Well, your explicit equation can start any way you'd like. You could say y equals, or f of x equals, or a equals for the amount. I'm going to do f of x because that's how we did it consistently in Unit 2, but like I said, you could use any other letter. So f of x is going to equal 1250 because that was how much she started with. That was what she had in the beginning. And then she needs a growth rate or a growth factor. This is actually the rate because we remember that the growth rate is a percent. So how did we turn a growth rate into a growth factor? Remember that we said it was worth 100% of what it was plus 4% more. So that would have been 104%. But then we want to turn that percent into a decimal, and that will equal 1.04. So that's our growth factor. And that's what needs to go in the parentheses of our exponential equation as the base, the pattern, the thing that we are multiplying by every time. And then we're gonna raise that to a power. We know it's going to be a 10-year bond. But although we know she's going to leave it in there for 10 years, we're just going to put an x for the exponent because we want to figure out how much it's worth after just 1 year or 2 years or 3 years. We're going to use our equation to help us fill out the table. And so we don't want to put a 10 into the equation just yet. If we were skipping to find out how much at the end, well, then we could do that with the 10. And so right now, we're just going to plug it in one at a time, or we can just think about this. How much did she invest in the beginning? Well, 1,250. How much did she have a year later? Well, we are multiplying by 1.04 every time. That's our growth factor, the thing in the parentheses. So if we were to multiply 1,250 by 1.04, we would get 1,300. And don't just add 50 every time because that is not what's happening. Now we're taking that $1,300 and it's worth 100% of the $1,300 plus 4% more of the $1,300. And so when I multiply that by 1.04, I actually get 1,352. Now that is worth, the next year, it's worth all of the 1,352, 100% of that, plus 4% more of the new number. And so when I multiply that, I get $1,406.08. Go ahead and round off like money. And you're going to run into decimals a lot when you do this, and that's okay. All right, so hopefully that keeps you going. You're going to just keep multiplying by 1.04 every time. Let's talk about Kaylee. So Kaylee must be loved twice as much, maybe, do you think? Her rate is the same as Cassidy's. She's leaving it in there for the same amount of time, but she got twice as much money to start off with. So then if our growth rate was 4%, our growth factor must also be 1.04, just like it was for little sister. And so our equation could look like f of x equals 2,500, because the thing that's changing this time is the amount of money they started with. The growth rate is the same, and that means the growth factor is the same for each sister. But they have different amounts of money to start with. Why do you think that would be true? Does Grandma really love Kaylee twice as much as Cassidy? Maybe we know that Kaylee is the older sister. Maybe Kaylee has less time to earn money because she has to go to college sooner. And so maybe Grandma gives her more money because Cassidy, maybe she's younger. We know she is younger. She's just going to sit back and let that thing earn money. And then maybe at the end of the 10 years, she can pull it out and put it back into another bond and keep earning money. But maybe Kaylee has to go to college as soon as the 10 years is up. I don't know. But that would make sense. So when we fill out Kaylee's table, again, we're going to start with 2,500. And then you're going to multiply that by 1.04. 100% of the 2,500 plus 4% more gives me $2,600. But we're not just adding $100 every time, because now if I find 104% of 2,600, I get more than $100 added on. I add $104. And then it starts increasing and giving me decimals. I get $812.16, and etc. I'm going to let you keep filling in the table. So then how does the initial value is the amount at the beginning, that was this. How does that affect the growth factor for number 3? Did that have any impact at all on the growth factor? No. That didn't change. That's why each sister had the same growth factor, because it doesn't matter how much money you start with. The growth factor is only affected by the growth rate. And so then how does the initial value affect the final value? In other words, how much does that money that we're starting with right here, how much does that have an effect on our end value? Well, if it starts higher, it's going to end higher. Now, something you might not have noticed, but I want to point out, is that Kaylee got twice as much money as Cassidy in the beginning, and every value after that is also twice as much. So you could see here that she had 2,600 while Cassidy had 1,300, and 2,704 is exactly twice 1,352. And if you look at the end of your tables, you can see that one is exactly twice the other. And that makes sense because she started with twice as much. She should end with twice as much. Yes, the initial value does affect the final value. All right, well, Cassidy's grandma also set up a fund for Cassidy's younger brother, Matt. So he must be the youngest. He's like the baby of the family or whatever. So he gets a totally different deal. And then Cassidy made this calculation to predict how much his fund is going to be worth several years from now. Wait, he got $2,000 and he was younger than Cassidy? What? Does she love boys more than girls? I don't know, maybe. And she's multiplying by 1.05. You know what that kind of reminds me of? I could maybe write this equation that the value is going to equal 2,000. That was our initial value, times 1.05, because it looks like that's the thing that we're multiplying by every time. That's our growth factor. But he only gets it left in there for 4 years because we're only multiplying it, 4 times. And so the initial value is 2,000. That's how much money Matt gets to start with. The growth rate, well, I know my growth factor is 1.05. I can see that right here in my equation, the pattern, the thing I'm multiplying by every time. You could also see it on the one that's written out above where there's a 1.05 written out 4 times. And so if that 1.05 is my growth factor, then 5% is my growth rate. And the number of years is 4 because we were multiplying 4 times. And so then on the back of your classwork, it says if the initial value continues to increase at this rate, then how much would he have in one more year? Well, you could just multiply that by 1.05 again, and you should get $2,552.56. But if you wanted to find out for 6 how much it's worth in 15 years, that'd be kind of gross to keep multiplying that way. So maybe it'd be way better to use our cool explicit equation and just pop a 15 in there for x and figure that out. And you should come up with $4,157.86, which is a great way to save for college. All right, now these kids have an Uncle Joe, and he's not as smart as his mom, Kaylee's grandma. He doesn't trust banks at all. He keeps all his money stuffed under the mattress on his bed. And so he's not earning any interest at all. He doesn't get compound interest. He doesn't get to find 100% of the money plus more. He just gets to add to his pile every year. So he's going to start off with $250 under the bed. And then the next year he's going to add $50 to that. So he's going to have $300, and then $350, and then $400, and you get the idea. So the reason I put this one in here is because I want you to see the difference between linear and exponential. You can see what it looks like in a table. In this table, you can see that we're just adding the same amount every time. And on the tables on the front of your classwork, you could see that we were not adding the same amount every time. And then on the graph for Uncle Joe, it's going to start at 250. And yeah, we're just adding 50 each time, like this. And I want you to think about the graphs that we've made for the King's Plan. You know, remember with the Rubas and all of that? Did those graphs look like this? No, those graphs, they curved. They were like, you know, I know they were dotted, but the same idea. And so we're just comparing and contrasting. What does exponential look like? What does linear look like? So Uncle Joe is linear, and Matt and Cassidy and Kaylee, they were exponential. Okay, so let's just write an equation for Uncle Joe, just because I want you to remember how to write an explicit equation for an arithmetic sequence. Well, we're going to start that off with f of x, or you could say y, or you could say a for amount, like it says in the table. Doesn't matter. Y would not be for year, though. It would be for like x comma y, like the y-axis. Okay, so f of x equals, how much did he start with? $250. And then every year he was adding 50, but that's got to be x minus 1, big, not an exponent. And you remember that you multiply first, because we are adding those 50s over and over again, but we didn't add a 50 the very first year. He just put that 250 under his bed and let it sit there for a year before adding 50. So you're not adding it as many years as you have. Okay, so how does Uncle Joe's plan compare to Kaylee and Cassidy's? I've already talked about. Uncle Joe is linear. It's more like an arithmetic sequence. The graph is a straight line, whereas Kaylee and Cassidy, their money is going to grow faster because it's exponential, and their graph would have a curved shape to it like that increases very quickly. Okay, on to your homework. Homework right here. Let's look at these tables at the very beginning. Number 1, it gives you this explicit equation. These are all explicit equations. Anytime you have an equation where you can plug in a number for x and it will spit out your answer, that's an explicit equation. So all you have to do is, one at a time, substitute the value for x into the equation and figure out what it is. So I'm not going to do the entire table for the very first one, but I'm just going to show you how it would look. You're going to say y equals 17, but instead of x, it's going to be 3 minus 28. And then you calculate what that is. Oh, my bad, that's a negative 3. Sorry, roll it back. Negative 3. Okay, so 17 times negative 3 and then minus 28. and you should get for your answer negative 79. And so in your table, next to the negative 3 would be negative 79. And that would also represent a point on the graph, negative 3 comma negative 79. That's what you're finding. You're finding these values that you could put on a graph. You're seeing them in the table, and you're using the equation to get there. So we're going to use all three of these representations over and over again. Let's talk about the table on number 4 because of my instructions not to use any decimals. And I'm doing that for a reason, not because I'm trying to be a pain in the butt, but I think the patterns show up better when you look at the fractions. And so that's why I want you to look at the fractions so you can see some of the cool symmetries that are happening here. So for example, on number 4, I want to start actually with this row of the table. What are we doing? We're plugging in x, these numbers for x, so this would be 6 to the first power. Well, that's just 6. And so let's maybe go down to this one next. That would be 6 to the second power. That's not 6 times 2. That is 6 times 6, two of them being multiplied together, and that is 36. And so then you can see that you would keep going, and I know this isn't a 3 right here, but if it was, you would just multiply by 6 again. So maybe multiply by 6 to find out how many for 4, and multiply by 6 again to figure out how many for 5. But what's really interesting is when you start going backwards up this table, what's it going to look like when you plug in a negative 1? 6 to the negative 1 power. Well, we skipped something in between that would have been 6 to the 0 power, which equals 1. So then, if we had numbers that went like this, 1, 6, 36, you would say, well, I'm multiplying by 6 every time. So going back up this direction, up my table, then you must be dividing by 6. And so 6 to the negative 1 power is the same as 1/6. I'm dividing by 6. That's what that negative exponent tells you to do. It's actually like cross the line and change the sign, if you remember that. So then the next one up, if this was a 1/6, would have been a 1/36, like that. And then we have to go one more because it's to the negative 3, and so that's going to be 1 over 216. So just look for the patterns and write your answer with fractions, because I think you'll see patterns better if they are in fraction form. Because look at that. There's a 1 in the middle. There's a 1/6. I know you can hardly read this. And then a 6. There's a 1/36 and a 36. There's a 1 over 216 and a 216. Like, the patterns will show up. Trust me. Take my word for it. Okay, Maya. This is another kid with a really nice grandparent. Her grandfather opened a savings account for her, and he only put $100 in. And then he didn't add any money before or after that. Just like, welcome to this world. Congratulations for being born. Here's $100. And the money is going to grow at a rate of 4% per year. So let's figure out how much money she would have when she turns 10. Or every year in between there. So in the beginning, she has $100. And then if it's growing at a rate of 4% per year, well, that means that every year it's worth 100% of what it was the year before, plus 4% more. And that is 104%. But I want to turn my percent into a decimal so I can work with it in an equation. And so I'm going to divide that by 100 and get 1.04. That's my growth factor. 4% is the growth rate. 1.04 is the growth factor. So that's how we found, for part B, 1.04. If you go ahead and multiply everything here by 1.04 every time, you're going to start getting decimals, dollars and cents, $112.49, etc. I'm not going to do all of these because that would be so boring to watch me do. But in 10 years, she's going to be up to $148.02. Now, this is a very conservative investment, right? It's a small amount of money, relatively small, and it's only for 10 years, and it's a pretty small interest rate. But I wonder what would happen if you left that money in there for maybe like 25 years until she got, out of college. Maybe she'd have enough to buy a car or something. I wonder how we could figure that out. Well, let's write an explicit equation. And maybe we could use that to figure it out. F of x equals 100 times 1.04, because our growth factor goes in the parentheses. That's our pattern. And the 100 is our initial value, the amount we started with in the beginning. And since this is an in the beginning amount, then we're going to have, like it says, after any amount of years, I'm just going to say x. But that could have been like x minus 0. And that's telling me, since there's a 0 there, that I was using the 0 term to write that. Could we write a different explicit equation? Absolutely. I'm going to write another one just in case you want to remember how to do this. Let's use the let's use the 10th term. 148.02 is my 10th term. It's still going to be 1.04 because that's still my growth factor, but then this would be x minus 10 because I was using the 10th term to write the equation. And you could use any term you want as long as you write the index for it, like, which term am I using up there in the corner. All right. Let's talk about these movie tickets. I'm not going to do every one of your homework problems today. I just want to help you set up an equation. Let's say a movie ticket now costs $7. $7. And the inflation is causing those ticket prices to rise by 4.5%. That, my friends, is the growth rate. The rate is the percent. The growth rate is a percent. It's how much it's growing every year. And so it says at this rate, how much will a ticket cost 5 years from now? You could do that recursively and just keep multiplying and adding, like the 7th grade method. But it's so much more elegant to write an equation and just fly right to the 5th term. So I'm just going to help you write the equation. We could say that the f of x is going to equal 7 because that's our initial value. And, I got to turn my growth rate into a growth factor. Well, 4.5% is going to, plus 100%, because remember, every year those tickets are going to be worth 100% of what they were the year before, but then they're going to cost 4.5% more. So that's 104.5% more. And then to turn my percent into a decimal, I got to move that thing over twice. So that's actually equal to 1.045 is my growth factor. Whew, that's what goes in my parentheses, 1.045. And then since I started with the 7 as my initial value, I'm just going to have x minus 0, which is just the same as x because I used my 0 term to write this equation. And now I could use that if I wanted to find out how much it'd be worth after 5 years by replacing x with 5 or 10 or 30. And I'm going to let you do that. Okay, the last two are so important to understand. We're kind of comparing and contrasting linear and exponential the whole time. And I need you to be able to write an equation when I give you the graph. So it's not going to be that hard because you are so good at writing equations from tables. We've been doing this for over a month now. And most of you can just, without even worrying about it, look at a table and write me an equation. Okay, if you know that's your strength, then let's write a table so that you can write an equation from the table. So really all you're going to do here is pull out the values off of the graph and stick them into your table. Problem with this first graph is it's kind of hard to tell what the values are. So it's so small. So I'm going to help you out a little bit. The very first one that I'm going to use, I'm going to ignore these over here because they're just way too small to figure out. But when x equals 0, y is 1. And when x equaled 1, y was 4. I don't know if you can tell, this says 16 right here, so each one of these lines is 4. And so then the next one we're going to look at, this dot right here, this dot right here. Well, that's when x equaled 2 and y was 16. And then the next dot that's like the next row over is right here, and that's a 3 and it's a 64. So just by filling in the table, like always move from left to right, and you'll be okay with this. We got 0, 1, 2, 3 going down. What is happening on the right? What is my pattern here? Hey, I'm pretty sure that's just multiplying by 4. Do I know how to write an equation of a geometric sequence that multiplies by 4 and that my first term is 4? Oh, I absolutely do. And I could even, if I wanted to, use my first term as, or my 0 term, which is 1, and multiply that by 4 to the x minus 0 power. And hey, wait, what's x minus 0? That's just x. I don't even need those. And this 1 right here I don't even really need, because 1 times anything is itself. So I could just write that like this, y equals 4 to the x, and be done. Or you could have written this one as, like, let's use our third term, 64 times 4 to the x minus 3 power, because 64 is my third term. So I could do that way. And you could use the first term or the second term. I totally don't care. All right, that's the exponential growth. It's curving. It's getting very large very quickly. That's exponential growth. Now, 17 is not exponential. 17 is linear. But we're still going to make a table and see what we can see from the table. So we're going to go -2, -1, 0, 1, 2. I mean, we could throw in the 3 if we want it, because that dot's on there. So it looks like when x is -2, y is down here at -10. And it looks like when x is -1, that y is at -6. And when x is at 0, y is at -2. When x is at 1, it looks like y is at +2. And then we got a 6 and a 10. So, hey, can you see the pattern? What's going on here? Oh, I'm adding 4 every time. Well, if I'm adding 4, then it must be like an arithmetic sequence. And so I could write my equation to say f of x equals, let's use the first term. The first term is 2 plus, what am I adding every time? 4. And I'm going to have the big x minus 1 because I used my first term. So I could have written a different equation with this also if I wanted to, like we've been doing with geometric. I could say, let's use this row. So I'm going to use 10 as my value, but I'm still adding 4 every time, but this is going to be x minus 3 because I used the third term to write that equation. All right, you could write many different equations for those two at the bottom there. Good luck with the rest of it. I hope that helped.